All right. Then in the second part of lesson 2, we're going to focus on Newton's second law, his famous F equals ma equation. And the first thing we're going to look at is how we would describe Newton's second law in words. And that is exactly what I have described here for you. And we will see that that statement is nothing more than saying in words what the equation A equals net force divided by mass is stating. So if you are asked in words to describe Newton's second law, you will take F equals ma, you'll solve it for A, and then literally you will just read in words what the equality is telling you with respect to proportionalities. So if I look at this equality, it is saying that the acceleration of an object, of a mass, the acceleration of an object is directly proportional to the net force. So then if the net force is doubled, the acceleration is doubled. If the net force is tripled, the acceleration is tripled. Directly proportional. And it is inversely proportional to the mass. So if I double the mass, then the acceleration is cut in half. So hopefully that will keep your verbal description, if you're ever asked to write down or describe it in words, what is Newton's second law. Don't try to make up your own description. Use the equation, read the equation. The last thing we see from this top description in our notes is that Newton definitely established a cause and effect relationship by introducing the notion of forces. The effect is what we see. When we see the force due to gravity pulling down on an object, we don't literally see the force. We literally see the acceleration, the object falling down, and we deduce or understand the cause by looking at the effect. Okay. Units. For our units for force, we now can put them in our base SI units, metric system. Mass is in kilograms, acceleration is in meters per second squared, and that is called 1 Newton of force. So 1 kilogram meter per second squared is 1 Newton of force. And in terms of the British system, our pounds, which is also force, remember we had talked about mass being in kilograms, or that British unit slugs, we can now calculate how big of a slug we are, because a person who weighs 220 pounds, force equals mass times acceleration, standing on the surface of the earth, will undergo an acceleration of 32 feet per second squared. That's the equivalent of 9.8. And when we solve for mass, we will see that a 220-pound person is actually a 6.87 slug. So the kilogram is for SI, and slugs, which again no one uses, but if you would like to calculate how big of a slug you are, take your weight in pounds, divide it by 32, and that is how big of a slug you are. All right, or your inertia in slugs. How about mass? So what's the effect on mass? Well, it's just what we talked about, being inversely proportional, but it can be dramatic. So if we take a 10 kilogram mass and a 100 kilogram mass, so a factor of 10 bigger, and if, for example, in this problem, we allow 10 newtons to act on both, so the same 10 Newton force acting on both, well, that inertia property of matter is 100% real. So the inertia property of matter is saying that the effect we see from an identical cause, 10 newtons, will give us an acceleration of 1 meter per second squared on this 10 kilogram mass. And look at this effect. So now inertia has really kicked in. Nature is saying, nope, that 100 kilogram mass is not going to display the same effect. Okay, the last part of this lesson is to look at a specific numerical example and see how we will apply Newton's second law to some basic problem solving, and that is what we're going to do. All right, so in this problem, we are looking at a hypothetical where we are taking gravity and friction and any other forces out of the problem other than these applied, made-up forces that we are given of 20 newtons pulling straight up and 30 newtons pulling down into the right at 30 degrees from the positive x-axis. So, the only way to ignore all those other forces is to hypothetically take it far away into outer space. And what we are going to do is say, well, if that's the case, that these are the only two forces acting on this 10 kilogram block, what would be the acceleration of the block? Well, just like when we did our two-dimensional motion and we separated our vectors out into x's and y's, forces are vectors. So we are going to separate our x calculation, which I have in blue here, from our y calculation, which is shown in red. And if we look at taking only the x's and y's, I'm going to take this F2 at 30 newtons, and typically I will always try to get my vectors off of diagonals, out of the quadrants and onto axes as quickly as possible if I need to do an analysis, and see that there is only this blue force F2 in the x direction going to the right, and then there's this red force F2 in the y direction going straight down. And once I've calculated those, so over here you see I have the 30 cosine 30 and the 30 sine 30. So once these are known, right? Whoops, wrong color. Once these are known, the blue one and the red one, I now will no longer use the full 30 newtons at all in my analysis, right? So what I'm going to do is just do my sum of the forces in the x direction equals mass times acceleration in the x direction. Notice there's no subscript on the mass. Mass is mass in both directions. And we will see that we get roughly 2.6, but I left a lot of decimal places there, but 2.598, 2.6 meters per second squared in the positive x direction. And now in the y direction I have to be a little careful because it's the sum of the forces. So I have 20 up minus the F2 in the y direction down, or the 30 sine 30. So here I get an acceleration in the y direction of negative 0.5. And we absolutely can just write that down and box it as our answer in Cartesian coordinates. Now if we were asked for the magnitude of the acceleration, then we have no choice. The magnitude of the acceleration is the Pythagorean theorem calculation of the 2.6x and the 0.5y to give us the overall acceleration. So if it's an overall acceleration question, I will plug it into v final equals v initial plus acceleration times time in this case, to get the overall speed, the magnitude of the speed at time t equals 3 seconds. If I was only interested in the x direction motion, if the problem was telling me, how fast is it moving in the x direction, then I would have used only the 2.6 in for the acceleration, and that would have given me just the velocity in the x direction. Now, in the last part of this problem, what we're being asked for is to find a third force that would equilibrate the system or make it such that there's no net force in either the x and y direction. And basically what we are going to do is use F equals ma to figure out what forces are in place initially, and then make whatever forces we have to make to balance them out. So in the x direction, F equals ma says that mass is 10 kilograms times 2.6, so I get 26 newtons to the right from F1 and F2, and I get 5 newtons up from F1 and F2 in the y direction. So that means to balance these out, I'm going to put 26, I'm going to make 26 to the left to balance the 26 to the right that comes from what F1 and F2 are producing. In that case, it's really only from F2, but we would add and subtract all of them if there were more forces. And in the y direction, I'm going to add a negative 5 down to balance out the 10 times 0.5 or 5 newtons up to make the F3 force, the force that is needed to make a stalemate of this system and have all of the forces balance out, be from these component forces. So we have a number of homework problems for you to look at, some multiple choice questions that should reinforce these concepts and give you confidence in your problem solving similar type problems.